In this video, the cycle we're going to be talking about is the refrigeration cycle, and then we'll also at the end mention the cycle that's used for heat pumps and what those are. So we'll talk about the refrigeration cycle in the context of the Carnot power cycle, which we've talked about quite a bit. So over here at the left, I have the Carnot power cycle. Right? In a Carnot power cycle, we can kind of think of the Carnot cycle is allowing heat to flow from high temp down there to low temp, and it's allowing heat to flow there, and we're kind of putting a barrier in its way of flowing, if you want to think about it like that, and that allows us to get work out of our system. In a refrigeration cycle, we're doing the exact opposite. We're putting work in and forcing heat to go from the low temperature to the high temperature. So how do we do that? Well, in the Carnot refrigeration cycle, we do it by flipping a switch and reversing all of our streams and reversing the function of all of our individual pieces of equipment, while still keeping the high temp and low temp the same. So you can see here, instead of going clockwise around the circle, we're going to flip the function of all of our devices and we're going to go counterclockwise around the circle. So we'll go from down here at the bottom, an evaporator, right? Before that was a condenser. It was taking a gas and turning it into a liquid. Now it's taking a liquid, turning it into a gas. So we flipped the function. We're taking that into a pump. We'll call this 1. We're taking that pump and putting it into, now not a boiler up here at top, we're putting that into a condenser. Then we're taking the outlet of the condenser, putting that into a what's now a turbine. So this is now low temperature and high pressure. And we're taking the outlet of that turbine and putting it back into an evaporator. So this would be what our Carnot refrigeration cycle looks like, right? It's, in essence, we're taking heat and pushing it from low to high temp, and we're doing that by having a network into our system. You want to think about it like that. I'm going to erase that just so I'm not muddying up the picture. We'll erase those last drawings. So again, so we're not kind of confusing with what the picture we have there at the right is. The way that we've looked at these cycles a lot is on a TS diagram. And right, what we know about Carnot on a TS diagram is it looks like a box. Not a very straight line. Here at 3, down there at 4, and back over to 1. So Carnot looks like a box. It's really defined by the high and low temps. And as we might expect, our reverse Carnot, or our Carnot refrigeration, also looks like a box. We start here at the outlet of the evaporator, go through our pump, up to high pressure, high entropy. Then we go through our condenser. We stay at the same temperature, but we're reducing the entropy because we're losing heat. In this case, right, we're losing heat, QH, to our high temperature surroundings. Then we go through our turbine here at 4, and then back over to 1 through our evaporator. So the system looks essentially the same, except instead of a network out, we have a network into the system because we flipped everything. Now you might expect this has really the same exact problems that the Carnot power cycle has. So this has the same issues as the Carnot power cycle. And that renders the Carnot refrigeration impractical. Or at least if we were to try to design something like this, it would be very far from the Carnot power cycle because our turbine and our pump would not work very well. So we have some of the same issues that we would have with a Carnot refrigeration cycle that renders this impractical. And so similar to how in a Carnot power cycle we said, well, let's make some concessions to reality, to things that we can actually design, and let's design the Rankine power cycle. We're going to do basically the same thing here for refrigeration. So now we're going to talk about the ideal Rankine cycle, or the ideal refrigeration cycle. It's sort of like a reverse Rankine cycle. It's a little different, and we'll get into that. We have, again, 4 processes. We'll start here at 1. So from 1 to 2, we're going to compress vapor across a compressor. That's our compressor. The compressor has some power input or work input WC. And again, this is the ideal refrigeration cycle, so this is a delta S equals 0. That's a delta S equals 0 process. From 2 to 3, this is our condenser. Right, we are rejecting heat. Right, this is we're losing heat now to our high temp reservoir, TH. If you think of a refrigerator, we're losing heat to the kitchen. We're doing that by condensing so when that happens, we're condensing our fluid. So we're going through our compressor as a gas. Then we're going to cool down and condense to here a liquid. So here we have a gas. Over here we have a saturated vapor. Should be X equals 1. 2, we have a gas or a superheated vapor, more specifically. Here at 3, we have ideally a saturated liquid. So that's X equals X3 equals 0. And again, this is just the ideal refrigeration cycle. Practically, we don't necessarily have to have a saturated liquid at 3. It could be a vapor-liquid mixture or a subcooled liquid. But for the ideal cycle, it's saturated. And that step from 2 to 3 is, we'll call it P2 equals P3. So that's an isobaric step, a constant pressure step, just like the heat exchanges in Rankine were constant pressure. From 3 to 4, this is where things get a little bit different than the Rankine cycle. And from 3 to 4, we're going from high pressure down to low pressure. We do that across an expansion valve. Right? If we think about what that would look like in a Rankine cycle, this would be, well, in a Rankine, there would be a pump on this side, how we've typically been drawing it at least. So the opposite of a pump would be a turbine. So in a Rankine cycle, we would have a real reverse Rankine cycle. We would have a turbine on this side. Practically, refrigeration cycles don't use turbines just because there's so little power that would be gained from them. So in reality, we use expansion valves. So this process from 3 to 4 is not a delta S equals 0 process because it's not a turbine. It is an expansion valve, so we're simply lowering the pressure. We're not capturing any of the thermal energy. We don't have any heat transfer. Ideally, we don't have any kinetic energy change or potential energy change, so our energy balance would just be delta H equals 0. So that's what we have here. This is a constant enthalpy or an isenthalpic process, if you want to have a fun word to say. So this is a constant enthalpy process, where the enthalpy at 3 is the same as the enthalpy at 4. Then from 4 to 1, we are going to be absorbing heat from our low temperature reservoir. This is our evaporator. So that's where we're going to be gaining heat from the surroundings. If we look at what this looks like on a TS diagram, we're starting, again, to scroll up a little bit, we're starting at the outlet of the evaporator. We're going through a compressor, so that's going to get us up to higher temperature and higher pressure, but the same entropy. Then we're going to be cooling this down and then going across the condenser to here at 3. Then from 3 to 4, this is the one that's kind of weird. This is so an isentropic process, a delta S equals 0 process would be a vertical line. A delta H equals 0 process is a little bit of a crooked line. So the ideal refrigeration process doesn't have two delta S equals 0. It has a delta S equals 0, P4 equals P1, 2 constant pressure processes, and then this constant enthalpy process at the valve. We characterize the performance of a refrigeration cycle a little bit differently as well compared to a power cycle. In a power cycle, we're interested in how much work did we get out and how much heat did we have to put in. In a refrigeration cycle, we're interested in how much work did we have to put in, so the net work that we had to put in, and how much heat did we take from our cold environment. So the coefficient of performance, sometimes called the COP, the variable that was a bad one. The variable that our book will use is beta, or COP. They call it both the same thing. The coefficient of performance beta is equal to, right, just like in a power cycle, the efficiency we defined as what we want over what we had to put in. We wanted work, we put in heat. In this case, what we want is QL. What we had to put in was WC. Okay, so one of the kind of neat things about a refrigeration cycle is because you're moving heat, you're not converting work to heat or heat to work. You're just moving heat from the low temp to the high temp. We actually can be more efficient than 100%. So real refrigeration systems can be have coefficients of performance of 2 to 3, maybe even up to 4, which would be, right, in an efficiency standpoint, 200, 300, 400% efficiency, which feels a little bit weird. That's why we don't call it an efficiency directly. We call it a coefficient of performance because we're not converting, right? This doesn't violate the first law of energy or the first law of thermodynamics, the energy balance law, because we're not converting heat to work or work to heat. We're using work to move heat. That's the distinction. Where in a power cycle, we are doing a conversion process. Here we're doing a moving process. If we do the exact same thing, WC, QH, QL, literally the exact same system, but here we have okay, TL and TH in a refrigeration cycle. We're focused down here. In a heat pump, we have the same thing going on, but our focus is up top. Okay, and what do I mean by that? Well, in a heat pump, for example, we can use heat pumps for home heating instead of a typical furnace. In a furnace, we're taking chemical energy like natural gas and we're burning it to generate some amount of heat, Q. In a heat pump, what we can do is we can use work to move heat from outside of the house to inside of the house. So our TL, that would be the environment outside. TH, that would be the environment inside of our house. We run the same cycle as your AC unit would run, but now the hot part of that system, instead of being outside the house as it is with AC, the hot part of the system, QH, is now inside of the house. So the difference between a heat pump and a refrigeration cycle is just your perspective. And by refrigeration cycle, just write AC because right, we could use this as a refrigerator, we could use it as a freezer, we could use it as an air conditioner. The only difference in all of those systems, again, the system is the same. We're designing it to operate at different temperatures. And we do that by operating at different pressures and at using different fluids. And if we go back up to our little phase diagram, we can change pressure. That will shift our temperature up or down for the system, right? It will shift our TL, it will shift our TH if we change pressure. It will also shift our TH or our TL and TH if we change where our phase diagram is. So if we, had it somewhere down there, then we would have maybe a system like that. Okay, which would also give us a different high temp and a different low temp. But the difference between a heat pump and a refrigeration cycle is only which side, the hot side or the cold side, you happen to be looking at. So we can very easily go back and forth in the analysis of a refrigerator, of a heat pump, and you might imagine we can actually design systems that are both. So we can design for homes. These are becoming more popular because instead of being 100, right, ideally a furnace would be 100% efficient. A heat pump could be 200 or 300% efficient. So they're more energy efficient because they're not generating heat. They're simply moving heat from one region to another. So we could design a a combination AC unit heat pump. You can actually find these on the market. They're becoming more prevalent, where we're taking a cycle like this, and then we have, a different plumbing, but we use the same equipment. We have the same evaporator right down here. The same condenser. We're just flipping really which side of the system we happen to be looking at. Now the only real difference is how we define the coefficient of performance. We call this beta prime. Again, how we define efficiency, how we will define coefficient of performance is what do we want divided by what did we have to pay for, or what did we have to put in. So in this case, what we want is we want our heat to go to the high temp, and we again are paying for our work. So it just changes based on what exactly we're looking at. It doesn't actually change in the analysis. It doesn't change in the design of the systems. So that's why we can make some of these types of combination AC heat pump systems, which again are becoming more popular because of that increased efficiency. Because you're not generating heat, you're simply moving it.